So in example 8, we looked at the situation where we were moving, so we knew that friction was equal to mu r. Now this example is going to deal with a situation where the object is not moving. So this calculator is stationary, and I can apply a force here. And if I apply a small force, which I'm doing now, the calculator will not move because friction will stop it from moving. I can even apply a little bit of a harder force and still friction is able to cope with that. But when I apply a great enough force, it is too big for friction. I can overcome the friction and it will move. Now, there are 3 different situations going on there. And I like to think about it as me doing an arm wrestle against several different people. So if we start off by thinking about if I was arm wrestling a small child. So when I'm arm wrestling a small child, I'm not going to actually arm wrestle them. I'm going to match whatever force they put in. So I'm going to, however much they try, I'm not going to lose to them, but I'm also not going to just snap that child's arm off and win their arm wrestling match. I'm going to humour them. So I'm going to balance with whatever force they're able to put in. And sure, I could put more force in, but I'm not at that moment in order to make it balance. Then let's say we swap the small child out and we put someone equally strong in. And I put all my energy in, and if I put all my energy in and put my maximum force in that I can muster, I don't win, but I don't lose. We're in equilibrium because we both have the same force that we're able to put in. And then of course, someone much stronger comes in, would be the third scenario, and they overpower me. So I put my maximum effort in and I hold them back a little bit, but because they're much stronger than me, they overcome me. And this is essentially what's happening with friction. So when I put a small force in, the friction matches my small force. When I put a slightly larger force in, the friction continues and changes with the force that I'm putting in, until the point where I put such a great force in that it overcomes the friction and the object moves. What does this look like mathematically? Well, actually the formula that I showed you earlier for friction equals mu r, is actually the maximum possible friction. So we're going to call this friction max equals mu r. And when is friction at its max? And if it's moving, it will be at its maximum, or if it has to be. Okay, so much like the example of arm wrestling a small child, we're not going to be at maximum friction unless it's absolutely necessary for the friction to be at that amount. Right? We can't have the friction be greater than the force it's putting on it. So let's imagine that friction was always at its maximum. Well, actually, when I push here, what you'd get is the calculator magically moving towards my finger because the forces would be unbalanced. So in order for it to stay stationary, friction has to match whatever force I'm putting in. It has to be an equal amount. So let's have a look at what it looks like in this question. So this question gives us a scenario, and it tells us that there's a block of 5 kilograms resting on rough horizontal ground. So we've got our 5 kilograms. And it tells us that mu is 0.4 and force P is being applied this way, and therefore friction will oppose that way. We've got the 5G going down here and then the reaction going straight up. So what's going to happen is it tells us that the different values of the magnitude of P and asks us what the frictional force acting on the blocks will be. So the first thing we're going to do is we are going to resolve it vertically. That tells us that R is equal to 5G, so that gives us R equals 49 newtons again. Then we're going to resolve it horizontally. And for us to resolve it horizontally, we need to know what the maximum value of friction will be. But because we've now got R and we've got mu, we can do that. Right? So friction max possible value, right, is going to be 0.4 times 49. This tells us that the maximum possible value is 19.6 newtons. So, when I've got a force of P in part A, which tells us that the P is going to be 10 newtons, well, if you've got 10 newtons pushing to the right, that is under the amount of friction possible. So friction, so when P equals 10, friction will equal 10, and the acceleration will therefore be 0. right? It will not move, it will be in equilibrium. So again, this is like the small child. Friction can go up to 19.6 if it needs to. But in this case, it doesn't, because their force is only 10 newtons. So what friction will do is match that force and prevent any movement. Part B, we've got that P is now equal to 19.6, which is at the maximum value of friction. So again, friction is able to match that just about, and there is no acceleration. That one is very similar to the example I gave about the man of equal strength arm wrestling me. Right, I can cope with it. I can stop him from winning. I can't win myself. Can't do anything more. I'm right on the edge. If he puts any more force in, the object's going to move. But at the moment, we're matching, and this is actually called limiting equilibrium. This is when friction is right on the edge of its maximum value, and any more, and we will move. So limiting equilibrium. The final one is when P goes up to 30. And of course, when P goes up to 30, friction can't cope. Right, so the force is going to be the P minus the friction, and friction will be doing its best, but its best is only 19.6. So it cannot stop the movement. We get 10.4 newtons from the force. We do F equals ma. We get 10.4 equals 5a. So a is 10.4 divided by 5, which is going to give us 2.08 meters per second squared. Okay, for 3 significant figures. Always give your answers to 3 significant figures in mechanics. Alright, so that's the 3 different scenarios of friction. It's important to understand basically that this mu r is when friction is at its maximum value, and if it doesn't need to be, friction will just balance with whatever force to prevent movement. And we've introduced this expression limiting equilibrium, which we're going to see in a setup to a lot of questions going forward from this point.